Okay, in this video, we're going to talk about Math 2320 project number 1. In this project, we're going to look at 3 different numerical methods for solving differential equations. In your later engineering classes, you're probably going to have to program these methods. But in this project, there is no programming. We just want to look at basically how to solve it, the name of the techniques, and look at how the numerical version differs from the exact solution. So, in the first part here, I'm going to go through an example to show you what I expect from you. So, we have an example here of a differential equation. dy dx is xy plus y, and the initial value is 3. So, first thing we want to do is look at the flow field. Alright, so I used the link for the flow field. I entered in xy plus y, and I generated the flow field. And I just picked these over here. You can't change those. That's just basically different starting initial values. They're not really important to what we're doing, but what is important is just to kind of look at the flow field, look at how these direction arrows look, and our initial starting off value was y at 0 is 3. So that would tell me that over time it's going to be moving up in that direction. So you're going to take a screenshot of your flow field and paste it into your PDF file. Alright, we want to describe the flow field. So looking at the flow field, I'd like to know, when is this thing 0? Well, factor out the y. So when y is 0, the derivative is 0, and so the function would remain constant. And if x is minus 1, that's also 0. And you should be able to see that from the flow field. You see here, if y is 0, it remains 0 for all time. And if I'm at x equals minus 1, see here, here's minus 1 for x. The derivative, or the slope, of all these flows is perfectly flat. Alright, so next we're going to look at the Euler method for solving this. I'm going from 0 to 1. Step size is 0.1. I used Wolfram Alpha to do this. So you type in exactly as I've typed in here for your problem. And so you can see here's the problem, the method we're using. The step size is the increment moving forward. So we're going from 0 to 1 with steps of 0.1. And so if Wolfram Alpha does that, you can see here is the exact solution over 0, 1. Initial starting value is 3. And then here's the numerical one. And so you can see the error is kind of small in the beginning, but the error is getting bigger and bigger the farther we get away from the initial condition. And then these are the actual results at different x's, and the number of steps we took was 10. This calculates the y value, and it shows you the error from the exact solution. So you're going to do the same for yours. Take screenshots, paste them into your PDF file, and then send that to me. All right, we're going to do this for the improved Euler and the Runge-Kutta methods. So the only difference is you use the word improved. All right, so doing that, Wolfram Alpha calls that by another name, which is okay. Step size again is 0.1, going from 0 to 1. And you can see there the exact solution and the numerical one are pretty good there. Looking at the errors are really quite small. Even getting all the way to 1, error is 0.01. So again, cut, paste from Wolfram Alpha. You don't have to do any coding. Just type it in, cut, and paste. And then sort of observe what's going on so that at a future time when you have to do the coding, whether it's in C or Java, you'll kind of have a basic idea. And then finally, with the Runge-Kutta method, it's a fourth order Runge-Kutta. And so similarly, you look at the graph of the exact and the numerical, at least over the interval 0, 1, and it's pretty good. Let's look at the error. You can see the error is really tiny. If you remember on the improved Euler, we had, I think, 0.001. Now we're at 0.0002. So it's a much more accurate technique as we get farther from our initial condition at 0, y was 3. And so you're going to do the same basic thing. Here is the link for how to get the flow field. Yours is similar. You got xy minus y squared. Initial condition, you're going to get your screenshots. Same step size, 0 to 1. And then you're going to basically type this in for doing yours, improved, and the Runge-Kutta. So make it nice and neat with your results, your pasting, your conclusions, and then email it to me as a PDF file. All right, good luck, and I welcome seeing your projects.